Bonjour tout le monde à Vitrines 2020. My name is Gregory Frank, and I'm the founder of the nonprofit E2 Adventures. We are Quebec and Canada's leading industry field trip company. We work with plenty of aerospace companies from Bombardier, Air Transat, Air Canada, MDA, CAE, and many, many more in both official languages, English and Français. Since COVID-19, we went virtual, and now teachers and students can explore the industrial world from home and also from school. So what we're about to show you are some clips from our live experience to MDA's clean room in June 2020. Have you ever heard of MDA, the satellite company? You may have seen one of their works, the Canadarm, on Canada's $5 bill. Multiple classes joined from across Canada, and thousands of people can now participate and interact simultaneously. So if you're a teacher, let's show your students how theory applies in the real world, in mathematics, in science, in languages, or in social sciences. And if you're a business, let's show the next generation what makes your business so interesting and so special and so cool. I hope you enjoy. Thank you very much.
What do satellites in space have to do with 3D printing in Montreal? How are they both helping us fight coronavirus? And what does all this have to do with you? So let me tell you a little story. This is the planet Earth, as you can see. But the story begins in March 2020. And I just want to give you a point of reference from our hometown of Montreal. It's one of my favorite cities on the planet. As you can see, here's Pierre Elliott Trudeau Airport. There's Mirabel. MDA is right over here in the West Island. Polytechnique is right over here near the mountain. You see the Lachine Canal. It's a beautiful view. But I want to bring you to a city in China called Wuhan in Hubei province. So now we're going over the Pacific Ocean. We're crossing the Japanese archipelago here, and we're finally in Wuhan province. The real start of the story starts in a specific part of Wuhan. And that place is this. It's a wet market. Now I have a question for you, and you're going to see a question on your screen. And the question you see on your screen is, what were they selling at the Huanan wet market? You have 4 options. Simply click on the option that you think is correct on the screen. Were they selling meat, live animals, wild animals, or all of the above? I'm going to leave this open for just a few more seconds. We have half of people who responded. 3, 2, 1. So we see that 94% of the respondents have chosen all of the above. And I would say that you are correct. Meat, live animals, and wild animals were in very close proximity, which allowed the virus to leap from one animal to another and eventually find its way to infect us humans. Now, here's a question for you. How do we go from that market to the world? It's a big question. And to answer that question, I want to jump over to another map that might help us. And this map is a map of all the planes in the sky. So as you can see on this map, these are all the planes in the sky right now. You can even click on some of the planes and see exactly where they're coming from, Osaka in Japan, and where they're going, Guangzhou in China. Now, if I zoom out, you'll see on the left side all the planes going to and from different places in and around China. So this is Japan, this is Thailand, this is Papua New Guinea, and you know that on the other side of the ocean, right over here, it's the US on the West Coast, California, and Vancouver. So here's my next question for you. My next question is, after China, what countries were impacted immediately next? As we can see, 61% of respondents chose Thailand and Japan, and you are correct. That was the next place that the coronavirus jumped and leaped to right after. And you can see that it just continued to propagate from one airport to another all around the world until we find ourselves in the situation that we're in today. But I started with the question, why did the Surgeon General show us the mask? And why did we do that in March 2020? I'm going to show you the next map, which is ships in the ocean. And these are all the ships in the ocean right now bringing stuff between Asia and North America. And what happened is because China was impacted first, they started making a whole lot of these. This is an N95 mask. Because they were already making 50% of global production, they just kept buying everything. So when the coronavirus spread to other countries, these ships stopped bringing masks across because there just wasn't enough stuff to bring. Now, why am I showing you these maps? What does it have to do with satellites? Well, you can see in the text here, it says position received via satellite. If you look really closely, all the positions for these boats, all the positions for the planes, and the maps that we saw originally come from satellites in space. Now, we're very lucky today because we're with someone who designs and manufactures these things. Hold on a second, it's just loading. Come on, don't be shy. Ah, there we're there. These are all the satellites in the sky right now. And at this point, I'd like to ask Pedro if he can come on and tell us just a bit more about how these work, how they get there, and about your world.
Great. So, hi, everyone. We're looking at an image of Telesat 19. This is a telecommunications satellite. It's a Canadian-built satellite, and it's also a Canadian-owned satellite. We built this for an operator out of Ottawa, and this satellite brings communication services around the world, basically around the Atlantic, a little bit left, a little bit right, a little bit south. But this can provide communication at essentially a continent-wide level. Now, you see the box in the middle, that is filled with electronics. You see the solar panels. The solar panels provide power because you can't have an extension cord up in space. And then you've got some butterfly wings out the sides, and you've got a tower on the top. So the butterfly wings are reflectors, and those they're basically like a mirror, essentially. So a satellite, basically an antenna, will have a horn, which is like a flashlight, except instead of flashing light, it'll flash radio waves. And then those bounce off of the reflectors because the horn is small. And with a larger reflector, you can get your signal out to a bigger area.
Holy cow.
This is a satellite reflector, a relatively small one. But you can see I'm not straining a lot. This thing is pretty lightweight. And it's lightweight because it's expensive to put stuff into space. So this is built out of carbon fiber composite. You might think of it as the material that we build Formula One racing cars out of. And it's a material that's super stiff and stronger than steel for its weight. The other thing you notice, maybe you didn't, when you think of your Bell satellite, it's all a dish. It's all nice and smooth. And this one isn't. It looks like it's lumpy. But those aren't manufacturing mistakes. This was actually done on purpose. So we actually shape the beam to the shape of the country. So if you want to provide service to Canada, you're not going to make a giant circle that extends to the North Pole. So a lot of engineering and a lot of science and maths goes into producing these things. Behind me, we have an even bigger reflector. This one is peanut shaped, and it's about 6 feet across. And that's another typical way we make antennas like the ones you see in the image. Obviously, they have to be very precisely built. So we sometimes employ our little robots, like this one in the back that we use for assembly. So what Greg is showing is, not unlike the cartoon that we saw a moment ago, this is the actual photograph of the actual Telstar 19 satellite. Again, the reflectors you see there, the butterfly wings, those are packed tight for launch. And when they get into orbit, they have to deploy and get into position so they can do their job. What we're seeing here is radio testing of the final satellite. Everything's been assembled, the box has been put together, the antennas are on, and this thing is sweeping through, and it's actually talking. It's sending radio signals, and the facility that it's in, I've been in this room, this is in Palo Alto, California. We have a very similar one here just behind me. This room is about 100 feet long. You see the spiky absorbers, and the job that they're doing here is actually measuring the performance. This is the last test that you do before you launch the satellite to make sure it's doing what it's supposed to do. Now, the thing about getting to space is you've got to go on a rocket. and it's a bit of a bumpy ride. And the last thing you want is to build a beautiful precision satellite, and then it gets up there and it doesn't work because it got broken on the ride up. So before we send anything up, we've got to test it. And what we're looking at here is video of a Mars rover. It's being vibration tested. We have 2 facilities like this right here in this building. One of our vibration shakers can shake up to 43,000 pounds of force. And that's enough to simulate the violence of a rocket launch. And we have to test everything before we ship it. Another thing about once you get to space, it's not like it is down here on Earth. You've got extremes of temperature. There's a lot of radiation, but there's also no air. So we want to test and make sure that nothing funny is going to happen to our satellite when it gets up on orbit. So what you have here, this is, I believe, the Pumpkin in Palo Alto. It's a thermal vacuum chamber. And what you do is you load your space hardware into there, you shut the lid good and tight, and then you suck out all the air so that you're working in a vacuum. And then you heat and you cool. You expose your satellite to the temperatures and the environments it's going to see on orbit, and you make sure that it still works. So the temperatures during the day on orbit can go to plus 150 degrees Celsius, which is a nice warm oven for baking your lasagna. And at night, when the sun goes down, it gets very cold. Things can go down to minus 150 degrees Celsius. In fact, you see the satellite looks like it's wrapped in garbage bags. Those aren't garbage bags. That's actual thermal cladding that we place on all of our spacecraft, like you put a jacket on to make sure that it doesn't overheat or get too cold. So it's all fine and good to build something nice in this building, but then at one point you've got to get it up into orbit. And orbit's a funny thing. It's kind of like, how do things stay up there? Think of it as constantly falling, but falling just over the horizon. So in order to get up there, you gotta slingshot yourself up to speed. And the way we do that, since we don't have a long rope, is we use rockets. And the rockets have to achieve orbital velocity for their payload. So they're converting chemical fuel energy into kinetic energy. And Newton's laws you've all learned, as the mass goes out, the rocket goes front, action, reaction. And so Falcon Heavy is one of the largest launchers on Earth today, and this was its maiden launch. Incredible vehicle built by a company that's been in the business less than 20 years, but it's really revolutionizing the spacecraft industry. Many of the satellites we built here in this building will be launched on SpaceX launchers. Some of them go from California, some of them go from Florida, and some of them will go from French Guyana, and sometimes we launch from Kazakhstan as well. So it's really a global business. This is the Telstar 19 spacecraft, the one we were just seeing that was being tested. At this point, it's been tested, and here the launcher is separating it. So it's done its job. The taxi has delivered it to its destination, and there's just some springs that gently push it off, and then it drifts away from the launcher into orbit. And then it'll open up its solar panels, it'll unfurl the butterfly wings we were talking about with those reflectors, and then the little rocket you see on the back there will lift its orbit. We'll call it orbit raising, because the rocket gets it to about 250 kilometers or so, but then it's got to make its way up to what we call geosynchronous, which is much, much farther away. All right, so we've talked a bit about satellites, and I also mentioned that satellites aren't just satellites around Earth. Different kinds of satellites. Telecommunications is one, brings us all the TV stuff. There's also Earth observation, which is critically important. So this is a picture of a RadarSat constellation, and what this is this mission takes pictures of the Earth, but it doesn't do it with light. What you're seeing here is actually 3 of the RadarSat satellites on the launch adapter before they get packed into the rocket. These were designed and built, 95% of it is Canadian. They were built right here in this building. This is actually in our building. You have one satellite in the foreground standing up and the other one in the background lying down, undergoing some testing. You can see all of the racks of equipment and the operators in front of the screens monitoring as testing is going on. It's a very complicated thing. What this thing does for a living is it's got 2 giant panels that open up, and they take pictures of the Earth using radar. The fun thing about radar is you don't need light. So it'll take pictures of the Earth day and night through cloud cover in storms, and it can help find lost ships at sea. It can help tell you how your forests are doing. It can help farmers know if they've got need more water. Here, it's being packed up into the clamshell. That's what we call the fairing for the launch adapter for the SpaceX rocket. So that's one kind of Earth observation mission. And this will take pictures of 95% or 100% of the Earth's surface every day. And this is the third in line of radar sats that we've built, all in this building here. Another Earth observation mission is Copernicus. Is a mission that you see the funny pointy antenna halfway up the side there. Copernicus is an Earth observation mission, and that funny antenna with the sort of the orange cone on it, we've built a bunch of those here. In fact, we're shipping one out later this week. What it does for a living is it's basically a radar altimeter. It bounces radio waves off the Earth and times how long it takes for them to come back. And what that allows the Copernicus missions to do over time is to monitor sea level rise, among other things. So when you hear in the news that sea level is rising, how do we know? This is one of the satellites that does that job. And those antennas were built right here in Montreal.
Pedro, we have one question from Catherine.
Please.
She's asking, where do you get some of the materials to build these satellites?
That's an excellent question.
Absolutely.
Basically, there's three principal materials that are very common. There's the carbon fiber that I showed you. There's aluminum that the feed horn is principally made out of. And then we use a lot of titanium because it's lightweight and strong. The thing about a satellite is it has to be reliable. And so it's not, you can't just, order out of a catalog or go down to the hardware store. All of our materials have to be traceable. All of our equipment has to be traceable. So huge quality requirements. Many of the materials and many of the parts we have purchased here in Canada. Some things can only be found in other places around the world. So a big part of the satellite is designing and working with suppliers to build these things, and then make sure that we know everything about them. Every screw has to actually be tracked. Every billet of aluminum that we machine things out of has to be tracked. A lot of it does come from suppliers in Canada, but we work with people around the world. Another fun thing that MDA does is robotics. So I think you've all heard about the Canadarm. And the Canadarm is something we've been building for a very long time. And we actually have one in the building right now, part of it. This is a picture of the Canadarm. And you see the astronaut balanced on the end of the Canadarm. That funny end that he's standing on, this sort of rectangular thing, is the hand. It's called the Latch End Effector. And we're building one of those, rebuilding one of those right now. It came down on one of the missions from the space station. We're refurbishing it. We'll send it back up. But we didn't leave it empty-handed. We replaced it with one that we had refurbished a couple of years ago. So this is a critical thing. We could not have built the International Space Station without it. And Canada's very proud. Here's a Canadian astronaut balanced again on the Latch End Effector of the Canadarm. And he's pulling out a momentum wheel that he's replacing on the space station. So a lot of really fun stuff. Another kind of robotics, if we have time, is Mars rovers. And if you look at so there's the ExoMars with the antenna again, but there's also a second part to the ExoMars mission, and that's the rover. This one's recently been named Rosalind Franklin, after a very famous and important scientist. And if you look at all of the wheels and how they're hanging off with the chassis and all of that was designed and built here in Canada by MDA. And in this building, we did some of the final assembly and testing of that entire chassis. So we really do a lot of different stuff here.
So that was fascinating, Pedro. I don't want to ask questions. I would just rather keep hearing you talk, because I think the kids are getting so much out of what we're doing in Montreal. We do teach science, earth and space, and we also teach material science in grade 10. So you really hit on some really important topics, and I think that's reflected in the questions that the kids are giving you. So I just have some little questions to ask the students. You guys, if you put the answers in the chat box, I can open the chat. I'll keep an eye on it. Also, we can direct the questions to Pedro or anybody else on the panel. So you've heard a lot about satellites now, but nobody's mentioned where satellites are located. And this is part of your course. So can somebody tell me where you're going to find these satellites? In the exosphere, thank you very much, Elizabeth, that is correct. So we keep talking about these satellites being in space. Would you consider the exosphere to be outer space?
Pedro, can you tell us just what's behind you?
Behind me is Fred. Fred is one of our assemblers here at MDA. Fred's been working with us for a very long time, and what he does most of the time is he builds satellites for us, specifically antennas or other spacecraft. Today, Fred is helping us out with our protection and collection collective initiative, and he's building face shields for us. So this is the area that we've set up that allows us to build face shields to support protection collective and to get these into the hands and, more importantly, onto the faces of frontline health workers. So you see Fred is wearing a face mask, and Fred is wearing a face shield. And this is important because honestly, assembling the face shields isn't really complicated, but we want to make sure that they're clean and sterilized. So that's part of what's going on here.
Hi everyone. So like you just saw, there was a face shield and you saw that there are different parts on it. So there's a transparent reflective visor. And if you were looking closely, you probably saw that there was also a band that was holding that transparent visor. And at the bottom, there was a little black part. And so not the entire thing is 3D printed. Some of it is laser cut sheets. So the transparent part can't be 3D printed, but a bunch of the parts there are being 3D printed. So the black visor at the front, and I have one right here that I printed myself. This one here can be 3D printed, and that goes around your head like this, and there are little knobs here where the plastic visor is attached. And the bottom one also, those are 3D printed at home. And so you might be wondering, well, what's 3D printing? How do you 3D print things? If I move over here, you can see the printer, and right now it's printing the same part that I showed you a second ago. And so you can see, if I zoom out a little bit, you can see that you have the heated bed there, which is the black bed that it's printing on, and that bed moves up and down. And so when it's done a layer, it'll move down. And if I zoom in, the part that's actually moving, it's got a bunch of wires, it's a black and white part, that actually has one of those hot ends, that part that I showed you earlier inside of it. And so that hot end, you can just see the nozzle there. It's not the red part, but it's a tiny little thing that's sticking out. That part is going and printing layers one at a time. And so this has been printing for, I don't know, maybe about 45 minutes right now. And each part takes about an hour and a half. And so once you have the file, either the one that you designed yourself or the one that you got off of a Thingiverse, so there are other websites out there, but Thingiverse is a very popular one. Well, then you have to take it into a software. So this is the second part. First, you design your part. The second part of the process is moving it into what's called a slicer. And so like I said before, you're stacking your layers one by one to build your final parts. Well, you need the slicer to kind of tell the printer how to do that. So if I go over here, you can see that I've taken Baby Yoda, I've downloaded him, and I've imported him into this slicer. So this slicer is also free. This one's called Prusa Slicer, but there are a bunch of other ones. You can Google them. A lot of good free options available. And so in this one, you're going to go and you're going to tell the machine, well, all sorts of settings. For example, the layer height. How thick do you want those little layers to be? Do you want it to be extremely detailed, which means that you can almost not see the layers, or do you want it to be a little bit rough? If it's a little bit rough, you might think that's a bad thing, but it can actually lead to much faster print times. It can print a lot more material at once, which means you'll get your part a lot sooner. You can also define things like what material you're printing, the color, the diameter of that material. So these filament spools, there are different types and they all have different properties. And once you've done all of that, then you press slice and you'll get this sliced part here. So if I go and I zoom in on Baby Yoda, you can actually see those little layer lines that I was talking about. So if we just move to the edge here, you can see that suddenly this surface, which was originally smooth, isn't smooth anymore. It's now been separated in tons of little layers. And I can actually show you what those little layers look like. So when you're printing this, the nozzle is going to go and print it from the bottom. So at the beginning you have nothing. It's going to print its first layers and it's going to gradually build up that part like so. And to save some time, it's not necessarily going to build the part completely full. So you can see on the inside here, I've actually made it mostly hollow. So it's actually doing a lot of individual lines, which means that it's using less material, so it costs less to build. It's also much faster to build. And in the end, if you're doing like an aesthetic part, then it's not a big deal. You can make it almost empty. If you're doing a functional part that needs to be a little bit stronger, maybe you'll fill it up a little bit more. These are all things you can explore. And so once you've done that, you'll get your final print. And if you're happy with the way it looks like, then you can go down in the bottom right corner, press Export G-code. And G-code is actually basically a series of instructions. What you're doing is you're telling the printer is just a machine. It's a set of motors, it's a set of heating components, but it doesn't really know anything. And the G-code, you're basically telling it, well, to build this part, you need to move this way, and you need to heat up to this temperature. And so it'll follow those instructions to finally build your part. And then you get, if I go back to my rear camera, you can see, I can show one last time the printer printing. You'll get, there it is. So now it's following a series of instructions. So basically I've told the printer, you got to print up to this heat, and those are the instructions that you have to follow. So you have to move in that way to get your final part. And that's what the final part looks like.
And if you zoom out quite a lot, you'll see, there you go, the giant ring that looks like Saturn's rings. That's geosynchronous. That's where all of the telecommunication satellites live. The reason your Bell Express View satellite dish has to point at only one spot is because when you're there, you're at one spot relative to the Earth. It takes exactly 1 day for you to orbit. And so from the Earth, you're at a fixed spot. Other orbits, like low Earth orbit, are easier to reach, doesn't take as much fuel. You're going around faster. This is places where the space shuttle works or the space station works, and also a lot of new constellations of satellites work. Once your mission life is over, what you got to deal with up there is you're not fully in space, as Heather was mentioning. You've actually got a little bit of air resistance. And so slowly over time, your orbit will decay. The friction with the atmosphere will slow you down, and you'll actually fall into the Earth. Hopefully you'll burn up. The space station has to fire its thrusters about once a month to orbit raise. So it kind of like up, 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 and then slowly drifts back down. And then every month, up, 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 slowly drifts back down.
We started the live stream today by asking what satellites and 3D printing have to do with COVID-19. And the answer is a lot of things, but they include transportation and contamination. We saw how the virus spread through planes and how the boats couldn't catch up. That's why 3D printing is so important. Also, this entire transportation system relies on satellites. They're created in clean rooms to prevent contamination, which could destroy the satellite. Like satellites, doctors and nurses are critical to the whole system, and they need to be protected from viruses. So what can you do today to make a difference? Well, let me show you. If you want to learn more about how you can get involved in your communities during COVID-19, sign up to volunteer with jebénévole.ca. It's a government website, and I know that a lot of you are at home for the summer, but this is a great opportunity for you and your family to get involved in the same way that Paul and Pedro are. Now, you might not have a clean room at your home, and you may not have access to a 3D printer, but there are plenty of places that need your hands over the summer and in the near and medium future. The second thing that might be interesting for you is to actually start doing CAD designs at home. So if you want to learn how to use computers to solve problems, like the 3D printers that we saw with Paul, you can just download Fusion 360 software in your computer. It's free, and it'll give you, and not only can you design cool stuff like visors, but really anything that your mind can come up with, which includes freaking Baby Yoda. Like, how cool is that? Anyways, it was so cool to see that. We'll be going on a lot more live streams next year. We'll be visiting gaming studios, data centers, laboratories, and much, much more. Speak to your teachers about joining us again in the fall and the next school year. And on that note, I'd like to thank our speakers, Paul and Pedro. I'd like to thank our guest educator, Heather, and I wish you all a great rest of day. Thank you, everyone.